Hey everybody, Vade here. Today I'm going to be proving Euler's formula using McLaurin series. So let's get started here by writing out the McLaurin series for e to the x. So the McLaurin series for e to the x is just the sum from n equals 0 to infinity. It's better, I can write a better infinity there, of x to the n over n factorial. Taking it out of sigma notation, it'll just be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial plus dot dot dot. It's very important to add the plus dot 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 if you were using the equal sign, because a plus dot 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 means that it is infinite. And remember, the McLaurin series is not an approximation. Okay, it is the exact same. Okay, if I remove the dot dot dot, then this would approximately equal to e to the x. It's an approximation. Okay, of e to the x. It's a McLaurin polynomial. Okay. So if you want to keep the equal sign, we have to do the plus dot 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 to show that it is exactly e to the x. Okay. If not, then you can approximately equal it to a McLaurin polynomial. In this case, it would be degree 5. So that's important to understand. So now I want to find e to the ix. Okay, so really, hopefully you understand. You have an e to the something equal, or an e to the something equals to something to the n over n factorial. So it'll just be 1 plus that something squared over 2 factorial plus that something cubed over 3 factorial plus that something to the fourth over 4 factorial plus the something to the fifth over 5th factorial plus dot dot dot. So instead of the x here, it'll just be ix. So it'll be 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the fourth over 4 factorial plus ix to the fifth over 5th factorial, or 5 factorial, plus dot dot dot. So now, where do we go from here? Well, hopefully you see here that we are dealing with some, or I'm going to first sort of highlight these numerators here. Hopefully you sort of notice here that this is, we see parentheses, we see an exponent, we see some, two factors here involving I. Hopefully you know, using your knowledge, that I equals the square root of -1. Powers of I can actually be simplified. Okay, so what I mean by that is we actually apply the exponent to each of our factors here as shown with these arrows. This will then be 1 plus ix plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus I to the fourth x to the fourth over 4 factorial plus I to the fifth x to the fifth over 5 factorial plus dot 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 dot. Okay. So now I'm going to simplify I squared, I cubed, I to the fourth, and I to the fifth. Please do not write the square root of -1 here because, come on, this is algebra 2. You probably remember doing simplifying powers of I, but we want to keep it in terms of I when applicable. So sometimes, like for example here, I cubed is the same as -I. You can prove that by cubing both sides of this equation here, and you will get -I. So hopefully you see here that you keep it as -I. You don't do negative, then negative of negative square root of -1. Just doesn't make sense, especially since we have an I on this side. We're not saying e to the square root of -1x. That's just not how Euler's formula is presented. Okay. While yes, it would be the same thing, we use I. Okay. So in this case, it'll just be 1 plus ix, and then I squared is -1, so it'll just be minus x squared over 2 factorial. Then again, like I said, this would be minus ix cubed over 3 factorial. I to the fourth is 1, so it'll just be plus x to the fourth over 4 factorial. I to the fifth, that is just I, so it'll just be I x to the fifth over 5 factorial plus dot dot dot. Okay, so now what I want to do here is, since this is a sum, okay, what do you, and I mean, we have a subtraction as well. What do we know about addition and subtraction? We can rearrange, right? If we have 2 plus 5, that's the same as 5 plus 2. If we have ix minus x squared over 2 factorial, that's the same as negative x squared over 2 factorial plus ix. Okay, stuff like that. We can rearrange. Okay, and this is true for even longer sums, infinitely many sums. So in this case, how I'm going to do this is I'm going to just move all the non-I related terms, to the left side of this side of the equation, and then the I related terms to the right side. So what I mean by that is I'm going to just write, I'm going to separate them as 1 plus, or 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And then I'm going to just do a plus dot 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 here. Okay. Now the reason why I am going to do that is, and I'm going to separate it in parentheses here, is just because if you at least acknowledge the pattern here, for every opposite term, right, we have a non-I related term, then we have an I related term, then we have a non-I related term, then we have an I related term, then we have a non-I related term, then we have an I related term. This pattern will always be constant. Okay, so we can just assume that this is the pattern for the non-I related terms. So then for the I related terms, how do we find that pattern? Well, again, I'm going to separate this here. So I'm going to do plus, then we have an ix here. Then we have a minus ix cubed over 3 factorial plus then an ix to the fifth over 5 factorial, and I'm going to do a plus dot dot dot, because again, this is how it works infinitely. As you see the pattern here, which will be constant, we go I related, these are all our I related terms, right? We'll see an I for every other term, I related term for every other term. Okay, just like we see a non-I related term for every other term. Okay, so now if we do this, we can actually factor out an I. Okay, we can factor out an I. So we'll get, again, just 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And this should be a minus dot dot dot. And the reason why is because another pattern that hopefully you notice is that the signs are also alternating. Okay, this goes from minus, this goes to plus. If you don't believe me, just write more terms in this McLaurin series. Okay, you can then, like, if you think about the McLaurin series for like e to the x, the next term would be x to the 6 over 6 factorial. Then x to the 7th over 7 factorial. Then just plug in ix, and then you can go from there if you are having trouble seeing that alternating signs pattern. Okay, and in this case with our McLaurin series, right, the patterns will be constant. Alright, so then plus dot dot dot, and then I'm going to, how do I do this? I'm going to write some brackets here, just better notation, and I'm going to factor out an I. Again, I will be in, because I'm splitting up the non-I related terms and the I related terms, and I will be in every single one of these terms, so I'm just going to factor out an I. So then this will just be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Again, this should be minus, sorry about that, because it is alternating signs. So now I want you to see where we can go from here. Where can we go from here? Okay, take a second, pause the video, see if you can figure out where to go from here. Because I'll tell you what, this is technically correct. E to the ix does equal to this. But think about, what does this equal to? And what does this equal to? Okay, pause the video, see. Okay, hopefully you pause the video, gave it an attempt. If you're completely lost, then you probably should first learn about McLaurin series. Okay, you probably don't know McLaurin series. Okay, now this is the McLaurin series for e to the x. Okay, hopefully you know what a McLaurin series is. If not, you probably do not understand this video. Okay, so if you know the McLaurin series of e to the x, hopefully you know the McLaurin series for sine and cosine. This is the McLaurin series, or in this case, this would be the McLaurin series for cosine of x, and this would be the McLaurin series for sine of x. If you want to, justify this, we know that cosine of x equals to the sum as n equals 0 to infinity of x, negative 1 to the n times x to the 2n over 2n factorial. And then sine of x equals to sum n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And if you actually take it out of sigma notation for both of these, hopefully you see here that this will then just be the 1 plus, I'm going to use a different color here. Hopefully you'll see that this will be the 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. I'm going to write another term plus x to the 8th over 8 factorial plus dot dot dot, and hopefully you see here that this will then equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus dot dot dot. And this should be a minus dot 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 as well because alternating signs. Okay. So, yeah. This is, justification as to why this equals that. You can see here, just understanding McLaurin series. If you do not know what your McLaurin series, you should probably review it. I'm planning on making a video on that very soon. Okay, on proving the McLaurin series for sine, cosine, natural log of 1 plus x, power series. I'm going to do a bunch of that. All right. So anyway, we can say that therefore, we can say that therefore, e to the ix equals to cosine of x plus I sine of x. Pretty cool, right? This is not the only way to prove Euler's formula, but it is one proof that is kind of straightforward to understand if you know McLaurin series, okay, and some calculus, okay, because you learn about the McLaurin series, and which is just Taylor series at x centered at 0 in calculus. Anyway, before we end it off here, I do want to point something out, and maybe you've noticed this already. Now, first of all, Euler's formula is used a lot. Okay, it is used a lot throughout. Depending on what level of calculus you're taking, it will be used at some point in your calculus journey and beyond. This is a very applicable formula, very applicable. But one thing you can actually get out of this is the most beautiful equation of all of mathematics, which is Euler's identity. I want to take a moment to actually use it. We proved Euler's formula. Let's now prove Euler's identity. So let us plug in pi in for x. So we'll get e to the I pi equals to then cosine of pi plus I sine of pi. And hopefully you know enough trig to know that then this will just be e to the I pi equals to then negative 1 plus then I times 0, which is just 0. So I'm just forgetting about that. So we can say, therefore, e to the I pi plus 1 equals 0. This is the most beautiful equation in all of mathematics. not really, you can't really argue that. I mean, like, so many people agree with this. This is the most beautiful equation. If you find an even more beautiful equation, let me know in the comment section below. But again, yes, beautiful is subjective here, but a lot of people agree with this statement. Okay? Um, that not with this statement. This statement, like, it's a fact that either I pi plus 1 equals 0. You can even type that into your TI-84 calculator, and it'll also spit out -1, which is really cool. I'm talking about the statement that this is the most beautiful equation in all mathematics. That is argued, but I've not heard of anyone who's actually said it's not. But anyway, thanks for watching, and see you in the next one.